So I want to pick up largely where we left off yesterday. We were talking about CW structures. I want to take a little bit of a step back, though, and let's talk about homotopy. If we're doing equivariant homotopy theory, you knew this word was going to show up at some point. So the way I like to think about a homotopy classically is the same as what we'll do equivariantly. I want this to be a path of functions. So in other words, two functions are going to be homotopic if I can continuously deform one into the other, the usual sort of model that we use. And I want to use this to sort of motivate my homotopy in the equivariant context. So if f and f prime are two functions between G spaces, x and y, then a homotopy is a map x cross the standard interval into y, such that, well, the usual things that we'd have. F of x 0 is f of x, and f of x1 is f prime of x. And now, all I've actually done is copy the definition that you know. I need to put in the equivariance. And so for that, I need to tell you how does the group act on this. And so here, G of a point x t is going to be gx t. So in other words, the group acts trivially on the homotopy coordinate. This is an important feature, and it's one that was a little surprising to me at first, because of course I would have lots of choices. If you give me any way that the group could act on this, I could make sense of a notion of homotopy that does this. This is the one that matches a path of functions sense, though. And so the reason is as follows. If I look at the G maps from x to y, well, this sits inside the collection of all maps from x to y. So this is just all continuous functions. And actually, since I'm in the equivariant context, I can remember that this had an action of G and this had an action of G. So I can endow the set of continuous functions from x to y with an action of G. So I'll say that G times a function, when I evaluate it on a point, this is going to be G of f of G inverse x. Sometimes we call this the conjugation action. In other words, this G inverse here, well, it's the same as we saw actually when I talked about the function object, the co-induced G space. I can either produce a left action by acting on the right in a function's argument, or in this case, I'm acting on the left by the inverse, which swaps the variance when I'm looking at a general group. And so this gave me a left action of G on the set of functions. Of course, left multiplication also was a left action, and so I was just doing both of them. Now, if I look at the fixed points, then map G from x to y, well, this is the fixed points of the mapping space, all things. So one of the ways that we talk about this, as I want to push more into the categorical language, is I can say that I have different possible categories of G spaces. I have the one that we talked about, where this is the morphisms. It's just all equivariant maps. But I can also choose a category where I have more morphisms, namely all maps. But then the morphisms here are again G spaces. Now, implicitly, I'm using the fact that if you give me two spaces, then the set of maps between them also is a space. I can use the compact open topology. Then things like composition, all the things I want are continuous. So here, this is again a G space if X and Y are. And so my category here, this is then a space, not a G space. And so my ordinary category, top upper G, is enriched in spaces. The Hom objects are all spaces. I could also enrich in G spaces. It can be helpful to try or to use either of the formulations. And so when I cross with I here and I give I the trivial action, then the equivariant maps from X cross I into Y, well, this is the same as the ordinary maps from the interval into just the space of G maps from X into Y. And I'll leave it as an exercise to trace through why this would be the case, why I have this sort of a junction between I can either cross with the interval with the trivial action or not. On the other hand, I could also do this in the enriched context. This is the G fixed points of the space of maps. The space of maps has the ordinary adjunction. This is just, when I do the space of maps, this is just continuous maps. And I know that crossing with a space is adjoint to Homing out of the other factor. So if I didn't have the G's here, this is something that we know already from ordinary spaces. And this is true. Now I just have to take what are the G fixed points of both sides. When I take the G fixed points here, since the interval has a trivial action, I just end up mapping into the fixed points here. And that's the argument. So stepping through the bigger Hom objects makes this adjunction more transparent. It also tells me that this is my path of functions. In other words, I have continuously deformed an equivariant map, so an element here, to another equivariant map, but I've done so always stepping through equivariant maps. So it gives us the right notion. Okay, another way that I can say this and to sort of continue to introduce you to some of the categorical language, we can say that the category of G spaces is tensored over the category of spaces, in the sense that when I cross with a space with a trivial action, I have an adjunction like this. It's not the same that I would get it for G spaces. This one, the category where I use these Hom objects, works for G spaces as well. Okay. So I wanted to talk about homotopies because then I want to talk about obstruction theory. And actually, you really set the stage for me yesterday by talking about them this way. And our notion of obstruction theory is carefully tied to our notion of homotopy groups, our notion of CW complex, and our notion of homology. So sort of a series of things that I want to talk about, and they're all connected through the notion of obstruction theory. So I want to start with a straightforward example. Let's say I have a map from a sphere into X. And now, let's not even worry about the equivariant context. Let's just remember the classical context. So the sphere sits inside the disk, and I can pose the following problem. What is the set of lifts? Or of course, my Hom objects are spaces, so what is the space of lifts of my given map from the n sphere into X over the disk. So I'm calling it lifts because I've actually drawn it in this way. I also would probably call them extensions over the disk. So what is it? So this is what? Well, let's think about what does it mean to have the disk. So this map is fixed. And so if I can extend F over the disk, then F is null homotopic. And conversely, if F is null homotopic, then I have an extension over the disk. And any extension over the disk is a null homotopy of F. So the set of extensions is the same as, I can get rid of this, it's the collection of null homotopies of F. So it's recording for me a lot of information, but this is exactly the way all of obstruction theory works. I want to know, I start with a map from something in, and I want to know what are the possible ways I can extend over attaching a single disk. And the reason we like attaching disks is attaching disks corresponds to null homotopies of the previous thing. So if I build on this very slightly, now let's say, I really wrote this too big. So now let's say I have a space Y and a map from Y into X. And I want to consider the space I get by attaching to Y a disk. So of course Y sits inside here. So in other words, I'm attaching an n cell to Y. I can ask the same question. What's the space of extensions of F over attaching a disk? So this tells me exactly what it is. It's the same idea. So walk me through it. What are all of the extensions over the disk of F? Well, let me spell out what the space I'm looking at a little more is. Here I have Y. And then I choose, or I've given myself, a map pi from Sn-1 to Y. So I'll draw, here's Y. And then I have my Sn-1. And that mapped to Y. And then I'm gluing it onto its image here. And then I'll just put the cone in, so now it looks like a disk. So this is the setup that I have. And I have a map from Y into X. So how do I extend this over this disk? What do I need to do? I have to know that when I take the composite from Sn-1 to Y and then map into X via F, I need to know that this composite is null homotopic. Because think of what's happening here. This is exactly what you said. This is the image that I'm looking at. But then really I have a map that's from this sphere into here. And then I've mapped over via F to X. And I need to know that that's null homotopic, because the extension over the disk is the same as a null homotopy. So it's the same thing here, that the extensions I get are, again, now it's null homotopies. of f composed with pi. So this is the heart of all of obstruction theory, that I know that I have an extension. So in other words, I can ask myself, does there exist an extension? In other words, is this set non-empty? And this set is non-empty if and only if f is null homotopic. So in other words, this is an element, not yet in the pointed context, but it will be, this is an element in pi n, the nth homotopy group of x. And my extension exists if and only if that element is 0. Then I can start talking about it. Same thing here. I want to know, can I extend f over the disk? I can do so if and only if a particular element in the n minus first homotopy group of x is 0. All right. So when I do this equivariantly, we need to look at homotopy groups. And they have a little extra structure. And we also need to talk about our cells again. But so now let's just copy this. If I have a map, and I'll switch to the pointed context because it'll be easier for me later. So I have a map from G mod H plus, smash Sn into X. Now these are G spaces. This embeds into the disk. And I can again ask, what's the set of lifts? And the set of lifts here is the same as the set of null homotopies well, first of all, it's a set of null homotopies of f. But I can do a little better. That's too big. These are G equivariant null homotopies of f. Well, remember, the induction that we have here, what's the blue? Oh well. Our map F is a map out of something induced, because this space is homeomorphic to G plus smash over H Sn via the action map, since Hx trivially on Sn. So my map F is the same as an H equivariant map from Sn to IH upper star of x. So in fact, I could have rewritten this diagram and looked just at an H equivariant diagram. And now it looks exactly the same as what I wrote over there. So now I'm asking here, it's null homotopies of F, but this is the same. I should give a name to my adjoint map, F hat. So these were G equivariant null homotopies of F, but I could have just done H equivariant null homotopies of F hat. So all of these are describing for me the exact same thing. This is one of the reasons why this choice of cells is particularly nice. I want to understand, what does it mean to give a null homotopy of this? Well, to give myself a null homotopy of this sort of thing, that's the same as saying everything is just determined by the H equivariant picture. I want to go one step farther. Let's think of an equivariant map out of something trivial. So let's think of what is map H from Sn into IH upper star of x. Well, if you give me an element f inside here, then I know that f of h times a point s in Sn. Since it's equivariant, this has to be h times f of s. On the other hand, h acts trivially on the n sphere. That's what we've assumed. So this is just f of s. So an equivariant map out of the trivial n sphere, in fact, it wasn't important that this was the n sphere here. What was important is that the action of the group is trivial on this. An equivariant map out of something trivial has image in the fixed points. F of s is fixed by all the elements of H. Yes?
So will this going to be like smaller than just all the homotopies?
A priori, yes.
Okay. So the same as like what you had before.
Exactly. I would have a bigger space of all possible null homotopies, but then I would restrict to the G equivariant ones.
So if it was like the trivial action, then you get like the whole.
Yeah, I mean, it can actually be the case that this set is empty, but the whole set of that something can be non-equivariantly null homotopic, but the map is not equivariantly null homotopic. I'll do an example of that. That's actually a really important phenomena, that the equivariant maps could have interesting homotopical information, whereas the underlying map doesn't. So yeah, that's why at this one I'm being very careful to only consider equivariant maps. All right. So the space of equivariant maps is the same as the space of non-equivariant maps from the n sphere into the fixed points. Of x. And I'm never going to write the IH upper star when I talk about fixed points, so I'm just going to write this as the H fixed points of x from now on. Okay, so this is something that's taking place just in spaces. This one was taking place in equivariant spaces, but now if I look at what I'm seeing, these are equivariant maps from Sn into the H fixed points. Same thing here, these are H equivariant null homotopies, but I'm mapping out of something trivial. So the last thing that I get is that my lifts, Sn dn plus 1 into IH upper star x, my set of lifts is the same as a completely non-equivariant story, Sn into the H fixed points of x, dn plus 1, and the lifts. Okay. This is the story that obstruction theory already told us about. So by choosing this collection of cells, by choosing things of the form G mod H plus smash a sphere or smash a disk, I'm able to say the question of how do I extend over a disk is the same as the ordinary question of how do I extend over a disk, but in this case to the H fixed point set. So in other words, only look at the part of the space that H sees trivially and do my extension there. All right. So now I also already start to see that these are the homotopy groups that I'm going to care about. At some point, remember I said I'm in the pointed context now, whereas here I wasn't. This is a pointed map from Sn into the h fixed points of x. That's an element of pi n of the h fixed points of x. So my homotopy groups have much more structure. And if I want to talk about attaching cells or thinking of maps from CW complexes, I need to remember that this is a map from one of the prototypical objects into X, and it came from an element of the homotopy groups of the H fixed points. So I'm going to define the following. I'm going to say that pi n with an underline of x, well, this is going to be a functor. And it's a functor from the category, which I'll call OG for orbits, and I'll describe this in just a second, into abelian groups or pointed sets, depending on whether n is bigger than or equal to 2, 1, or 0. So this is the category whose objects.
What is that symbol in your definition?
What is which symbol?
It's a pi.
This one? This is a pi. It's an underlined pi. Yeah. The objects of this are going to be the orbits, G mod h, as h varies over all possible subgroups, and the morphisms are just G maps. I'm sorry?
Two H's give the same orbit type to you or not?
No, I want to remember the distinct isomorphisms. So in other words, conjugate subgroups produce isomorphic orbits. I don't want to identify them. I want to remember that I have an isomorphism because that isomorphism is an element here, and it's data that I want to record. In particular, the automorphisms of an object are going to act on the value of this anywhere. So what's it mean? And well, I haven't defined it. I just wrote down a symbol at this point. I'm going to say that pi n of x, when I evaluate it at G mod h, this is going to be the homotopy classes of maps from G mod h plus smash Sn into X. And I also see that I wanted this to be a contravariant functor, so I'll put an op here to control for the variance.
There's no action of G on Sn?
Exactly. There's no action of G on Sn. So the only things that have an action of G in this case, the G action here is entirely governed by this. The G action here is whatever it is. And so from the discussion that we had right here, yes. I'll put that to make sure we see it. So by the adjunction of induction and the forgetful functor, this is the same as H equivariant maps from Sn into X, and then this is the same as non-equivariant maps from Sn into the H fixed points. Yes?
So I'm missing why it's contravariant. Don't you just pre-compose with the map from G mod H to G mod K?
Exactly, and that's a contravariant operation.
Oh, okay.
So, no, you're exactly right. That describes to me the functoriality.
Okay.
That if you give me a G map from G mod H to G mod K, So if you give me something like this, then I can take this map at a disjoint base point and smash it with Sn. And that gives me a map from the homotopy classes G mod K plus smash Sn into X to the homotopy classes of G mod H plus smash Sn into X by precomposition. So right now I've written this, and it's perhaps a little opaque still, but I want to make sure we're all on the same page. Do you see why this is a functor? Basically what I've done for you is I've described the value of this on each of the objects. That's what this part did. And then the discussion over here tells you, what do I do on the morphisms? In other words, I'm just precomposing. In some sense, this is a Yoneda style embedding. I'm saying that I can embed the orbit category of G into the category of G spaces in a couple of different ways. And the way I'm choosing is to embed it in via G mod H plus smash Sn. And then I'm just taking Hom out of that embedding, and that gives me a functor.
Excuse me.
Yes?
What define your functor when n is equal 1?
If n is 1, then it's not abelian groups, it's groups. And if n is 0, it's not groups, it's pointed sets. I just was lazy in this case. But I would define it in exactly the same way. That the only thing that changes is the target and whether or not the target's commutative or not. So soon I'm actually going to restrict attention to things that are simply connected, in which case I will never again have to worry about the fundamental group or connectivity. All right, let's think about what these pieces are, though. And let's think about what a generic G map looks like. So these are orbits. We know what G maps out of an orbit is. Spent some time on that yesterday. So map G from G mod H to G mod K. Well, this is G crossover H with H mod H, so a point. And so by the adjunction, this is the same as H equivariant maps from a point into G mod K viewed as an H set, which is the same as, well, I can tell you the value of a function on a point by telling you the value of the function on that point. So this is the same as an H fixed point of G mod K. So what does that mean? That means I have a point with stabilizer H inside here. So let's write down a map that works. So if H is contained in K, then I know that, well, I have an obvious map from G mod H to G mod K. It's just the projection. It's the crush out a bigger subgroup map. So sometimes I'll need this map, so I'm going to give it a name. And I'm very much overloading the symbol pi, but I hope that there's no ambiguity later when we talk about it. So let's take this map and let's look at the upper star map associated to it. So let's hum out of this. So I want to compute maps from G mod K plus smash Sn into X. And we saw that this was the same as the nth homotopy group of the K fixed points of X. On the other hand, when I do G mod H plus smash Sn into X, this is the nth homotopy group of the H fixed points of X. And this map is the one that says crush out more of the subgroup of G. So in other words, don't just crush all the points of H, crush all the points of K. So if I translate that over here, this map is induced. So this is just the map pi n of the inclusion of the K fixed points into the H fixed points. So the set K is bigger than H. So anything that's fixed by K is necessarily fixed by all of H. So that gives me an inclusion of spaces, the K fixed points sitting inside the H fixed points. And so what this map, which I'm going to call for that reason the restriction, what this restriction map does is it says, tell me the image on homotopy of the nth homotopy group of the K fixed points in the nth homotopy group of the H fixed points. Okay, what do the other maps look like? Well, I have another option. And that is, it might not be the case that H sits inside K. It might be the case that H is conjugate to something that sits inside K. Then we have the same map. So if G, H, G inverse sits inside K, then I can view this as two maps. Well, this gives me a map G mod, GH, G inverse to G mod K, and then the multiplication by G map says that these are isomorphic. And that gives me all of the other maps. So this set is the collection of elements of G such that H is subconjugate to K, such that those elements of G that make that when I conjugate H by them, I get a subgroup of K. And then once I've conjugated, I take this map. So there's lots of things that I could do. But it's a relatively straightforward set. All right. So let's look at an example. Let's again look at G is the cyclic group of order 2. So let's look at the orbit category. Well, I have two objects. I have the orbit C2 mod C2, and then I have the orbit C2 mod the trivial subgroup. And I have a projection map. It takes me from C2 mod the trivial subgroup down to C2 mod C2. And I also have an automorphism of this that's multiplication by C2. So this is an order 2 automorphism. And that's it. That's the whole category. So when I have a contravariant functor out of that, like my homotopy group, so pi n of x, well, this is pi n of x evaluated at C2 mod C2. And I also have pi n of x evaluated at C2 mod E. I have my restriction map. And I have my automorphism. And this one was pi n of the fixed points. This one was pi n of x. This was the map induced by the inclusion. And since x had an action of C2, since x had an action of C2, I can just take pi n of that self-map of x. And that gave me the structure I had. This is everything. This is all the structure that the homotopy groups have. I've written down this already. I see my homotopy groups aren't groups anymore. They're diagrams of groups. This is sort of a two-edged sword. On the one hand, if I have a map between G spaces, so a map from X to Y, that induces a map of these diagrams. So there's a bunch of diagrams that have to commute. That means I put extra structure on it, and so it's harder to have maps because they have to commute with everything. On the other hand, I no longer have abelian groups. I have these diagrams. It's harder to compute with them because there's more information that I have to record. In general, even for things like, abelian groups, if I want to think of the homological algebra of abelian groups, it's really easy. Abelian groups have projective dimension 1. That everything has a resolution where I have at most 2 free things. It's because Z is a PID. You know this. Even in the case that I'm looking at abelian groups, once we stabilize, the projective dimension jumps to infinite. So there's a lot more structure here, but you lose a lot of the simplicity with the homological algebra. All right, now let's get back to the obstruction theory. And I need to talk about homology, because that's the natural home for obstructions. And I've already seen that this sort of structure is what's going to show up naturally. So I'll make a slightly more general definition, and that is that a coefficient system is a functor from OG up into abelian groups. So in particular, if n is at least 2, then my homotopy groups are the prototypical example of a coefficient system. Okay. So now our obstruction theory. Let's say I have started building a CW complex. So here I have my n-1 skeleton. And I have a map from my n-1 skeleton into some space Y. And in a minute, I'll be able to say these are G spaces, but let's just think in the ordinary space case. And I want to put in a few simplifying assumptions. I want to assume that everything in sight is connected and simply connected. Otherwise, I have to start worrying about the action of the fundamental group. It's the same sort of problem that you deal with the Sayre spectral sequence. At the end of the day, we write down the general form of the Sayre spectral sequence, and then we never apply it except in the case that everything in sight is simply connected, because that means that we can actually compute with it. Same sort of thing here. I want to just have a blanket assumption, everything inside's simply connected. So now I can ask the same thing I'd asked before. How can I understand, or how can I parameterize, how can I determine the collection of extensions over the end skeleton? So again, what do I need to do? Well, I get the end skeleton from the n-1 skeleton by attaching a collection of cells. And I know how to attach cells. That's the same thing as gluing a disk in via a map from a sphere in. And I know how to extend over mapping a sphere in. And I also know that the n cells here are as disconnected as they could possibly be, that the interiors of the n cells don't intersect. The only thing that could possibly change is what happens along the boundary, but we've already controlled what happens along the boundary because that took place in the n-1 skeleton. So to use the same notation I'd used before, I can understand this as a push-out where I've mapped a wedge, some big wedge of a set, Tn plus, smash, actually, once I've got the wedge, I can just leave it as a finite set, Tn plus, smash the n-1 sphere into this, and then the Tn plus, smash the n disk, sat inside here, and that was a push-out diagram. So to understand a map out of here, I just need, again, a collection of null homotopies, one for each of the wedge summands. So let me...
Tn plus means that base.
Yes, yes.
And also you have a base for Bn and for...
Yes, everything's based in this. Yeah, exactly. I'm in the pointed context.
Yeah.
So I assumed that my CW complexes are pointed and that F is a pointed map. So what I get is for each t in Tn, we get a function. We get an element of pi n of y, pi n-1 of y, given by the homotopy class of F composed with, and I forgot to give this a name, I'll call this En for the characteristic map for the n cells. So to say F composed with En, and then I'll never use this again, but I'll do it slightly abusively and say restrict this to the summand indexed by T. So in other words, I have a map Sn. This sits inside Tn plus n-1, Tn plus smash Sn-1 by choose, this is S0 smash Sn-1, and then a choice of point of Tn is the same as a map from S0 into Tn plus. So I choose that map.
Sorry, are you still in the non-equivariant context now?
I am. Yes. No, it's important because I'm actually just teasing apart points, so I don't want to be in the equivariant context yet. And then I map this into x n-1, and then I map to y. So here's F, here's En. And so this gave me a map from the n-1 sphere into y. I've actually made this harder on myself because I really should have just drawn this as a big wedge of copies of the n-1 sphere indexed by the points of Tn. And if I'd done that, then the statement restrict to the sum and indexed by T makes more sense. And this map is just include that wedge sum and into the wedge. Okay. So what is this? This is a function on the n cells with values in the n-1st homotopy group. That makes this a cellular cochain. In fact, what I've written down is a cellular cochain. It's a function from the n cells into pi n-1. And I'll call it, for no good reason, C of F. This is an element in, well, it's an element in the Hom group from the cellular chains, cellular n chains, into pi n-1 of y, which is the same thing as the cellular and cochains of x. Oh, that was terrible. With coefficients in pi n-1 of y. And so this is the setup that we have. I have an extension of f if and only if this cellular cochain is 0. That's a really harsh condition. In particular, it's not a homological condition. I'm making a statement that a chain is 0. But then there's two propositions that would take us kind of far afield, and they're not fitting the narrative that I want to tell. And that is that, first of all, this cochain is actually a cocycle. And second, if f is homotopic to f prime, then the cohomology classes of cone on f, or sorry, the obstruction class on f is the same as that on f prime. So this isn't telling me something about the actual map. It's telling me something about the homotopy class of the map. And I can even do better if I'm more careful. I can actually put various adornments here. Namely, I can control not just sort of abstractly homotopic, but I could say something like homotopic relative the codimension 1 skeleton. So these are maps from the n-1 skeleton. I could say it's homotopic relative the n-2 skeleton. So in other words, I just perturb on a single set of cells. Yeah?
Can you impose that they're equivariantly homotopy?
I'll get there in just a second.
What's the co-boundary? You said it's a co-cycle. So what's the co-boundary?
This is the cellular cochains. So it's the usual cellular co-boundary. I've taken the cellular, I just take the cellular cochains on X.
Now.
Yes, everything's cellular on X.
No longer this action. Just
Yes, everything inside. This is the ordinary non-equivariant picture, and I'm just in the cellular story where this is actually a piece of a cochain complex where I let this n vary and hold this n fixed. So that's a terrible way to say it. So the two n's play different roles, one of which I vary and the other I fix. So if I put this together, then I learn something really interesting about this map. Namely, I can't necessarily extend f. The extension of f is a much more rigid statement. It cares about the actual cochain. The extension of the homotopy class of f is a homological statement. It cares only about the cohomology class of the obstruction. So what I can do is if the cohomology class of the obstruction vanishes, then I could extend F. But maybe I had to perturb it. So maybe I had to choose something that was homotopic to F and then extend that. And what's in some sense miraculous about obstruction theory is I might worry as I'm doing this that I would see sort of a tree of possibilities. Namely, I have lots of things that are homotopic to F and lots of things that maybe I could do extensions over. And I would worry that anytime I chose one to do an extension, now I've gone up, and then I have a whole host of things that show up. I would repeat the problem. And I don't know, does this ever terminate, or is there something I can actually do? It turns out you would only have to drop down a single level. That's what makes obstruction theory really miraculous. If you can extend up to something like the end skeleton, you only have to go a level or two down, and then maybe go back up. You don't have to go all the way back down to the bottom. So obstruction theory defines for me a sequence of obstructions, a sequence of cohomology classes, one for each F, and if they all vanish, then I can extend over. All right, so now I want to do the same thing, but equivariantly. So far, this is just the classical non-equivariant story. Exactly, this is what, this was, I don't know the entire history, but this was, this sort of argument was the one that I know Eilenberg and MacLean used to show that maps into an Eilenberg-MacLean space is the same as the nth cohomology. It's this sort of obstruction theory argument. You could do a bunch more that you can write down this homotopy produces for you an explicit element whose co-boundary is the difference between the two obstruction classes. So everything you have is actually very, very concrete. And, but I don't want to go into it. It's a really beautiful story. I just don't have time. Okay, so what are the things that are going to change equivariantly?
You know, this was done the classical. There's a paper in the. There was a very nice. It was a meeting where is it? In Michigan.
Mm-hmm.
And there's where Eilenberg.
Describe the sort of primer on obstruction theory?
Yes.
Oh, wow. I didn't know that. It's a beautiful topic. It's one that, I mean, I really love how it's very concrete, and I haven't done anything that's actually not very transparent from understanding. What does it mean to extend over a disk? All I've done is built on that intuition that you have. Extension over a disk is the same as a null homotopy. And then everything else followed from that. So in the equivariant context, I have to start to be a little careful. So what I want to do is I want to actually, I wrote it this way because it's very clean and it gives me a nice tight formulation. But what I want to do now is say, if you give me a finite G set, or in fact any G set, I can write this as a disjoint union of orbits. So alpha in some indexing set of G mod H alpha. Really, I should say this is isomorphic. There's not a canonical isomorphism that identifies these. It's one of the reasons why I want to write everything in terms of the finite, or not even finite, in terms of the G set rather than a collection of orbits. Here, I can make much more sense of naturality. I understand maps between G sets. They're just maps between G sets. This is likenable to choosing a basis. I had to pick an element in each orbit of the G set, and then I had to use the proposition from last time that an orbit in a G space or G set is isomorphic to an orbit in this description. So I had a bunch of different isomorphisms then. I could decompose this into the disjoint union of its orbits. That's actually a canonical isomorphism, because all I've done is choose. I haven't actually made any choices. I've just picked each element and then asked for the orbit of that element. So the choice that I made wasn't really a choice, because I don't remember the name of that element. I just remember the orbit that it generates. Here, I had to name every element. But in this case, it's actually going to help me a little. So now let's think of what does Tn plus smash an n minus 1 sphere look like? Well, this looks like a big wedge, and let me use a little bit of notation. I'm going to say that Tn modulo g is just the set of orbits of T. So in other words, I take Tn and I put the equivalence relation that G times T is T for every G in G. So this is a pretty brutal operation. But what this lets me do is it lets me count the number of equivalents, the number of orbits. This is in one-to-one correspondence with the set of orbits. So this is then the wedge over Tn mod G. And actually, I should say, this indexing set I, now I can rewrite it. I is actually Tn mod G. So I probably should have set it up there. So this disjoint union here becomes the wedge over alpha in Tn mod G of G mod H alpha plus smash the n minus 1 sphere. So in this case, I've chosen an isomorphism, so I've chosen a presentation of this finite G set. And out of that presentation, I got a decomposition of Tn plus smash Sn into things that we've spent some time dealing with, namely an orbit plus smash the n minus 1 sphere. So what does a map out of any of these factors look like? Now I can start to mirror what I saw before. Every single one of these, remember I should think of these as indecomposable. That although it's really a wedge of G mod H alpha copies of the n sphere, since the group is just moving those wedge factors around, from the group's perspective, it's a single indecomposable unit. This is the collection of how many n cells do I have, where now my n cells are disks on this. So let's start copying. I have a characteristic map in the equivariant context from Tn plus smash Sn minus 1 into Xn minus 1, and then I have my map into Y. Nothing changes here. So now let's think about what's happening over here. I want to define my cocycle. So for each T in Tn, well, now I have to be careful. If my two T's are in the same orbit, then I don't want to break them up. I want to view it as a single thing. So in other words, now for each T in, so for each alpha in Tn mod G, we have a map G mod H alpha plus smash Sn minus 1. This includes into the wedge of the G mod H alphas plus smash Sn minus 1. And then I can map that down to X n minus 1. So you should think of this as being just this map. Include that summand. But this records it in an equivariant way. If I tried to just include, this is a bouquet of spheres, if I tried to just include one of the wedge factors, I've lost all of my equivariance. Because when I apply the group to that, it lands somewhere else. It went into another sphere. On the other hand, when I apply the group here, it just moves them around. And I don't have any extraneous information. Every one of the spheres here comes from, say, a chosen sphere by multiplying by an element of the group. So when I think of my function, now there's two things that have changed. It's not just that for every n cell, I have a homotopy element. Well, now I'll compose down to y. This gives me an equivariant map from G mod H alpha plus smash S n minus 1 into y. In other words, if alpha is in Tn mod G, corresponding to an n cell, G mod H alpha plus smash an n disk, then we get an element of pi n minus 1 of y, and then the H alpha fixed points. Oh, sorry. Evaluated at G mod H alpha. That's what I want to say. So this is different in two ways. First of all, I wanted to remember that my summands, they actually sat in little orbits rather than in individual summands. And then second, now my cocycle doesn't actually take values in the same group. Cells that have different stabilizers land in different groups. So this is the notion of cellular cohomology that I'm going to end up having to deal with. I need to take my chains, I need a notion of cellular chains and cellular cochains. So I'm going to say that this is an element of the nth cellular cochains on X with coefficients in the coefficient system pi n minus 1 of y. So this is giving me an abelian group, but it's not necessarily the one I would think about. It's the one that says, if you give me this abelian group that I write down is the direct sum over all of the cells, so over all of Tn mod G, of the value of this at the stabilizer at that cell at G mod H alpha. Yeah?
What does a chain map between things like this look like? Like what commutativity does that satisfy?
Everything you would want.
Sounds like some weird, crazy three-dimensional thing. I mean, like you could draw it as a box.
Yes, you could draw it as a box. Yeah. When I have my map of chain complexes, this is actually, right now, this is actually just an abelian group.
Yes.
What I've written down here.
Yes.
So the chain complex is actually a chain complex of abelian groups.
Okay.
And then the commutativity that you see is sort of the expected one, that if I had a cellular map from X to X prime, then it takes the cells to other cells. So all it's going to do is actually take a G mod H1 to a G mod H2, and then, well, a map from G mod H1 to G mod H2 is an element in the orbit category. So it's telling me exactly how to evaluate on this factor. I'm going to give another version of this in just a second. It's a little more transparent. This is called Braddon homology. And I want to write it again. This looks like the direct sum over alpha in Tn mod G of pi n minus 1 of y evaluated at G mod H alpha. So if I was in the ordinary abelian group case, not this weird coefficient system case, this is exactly what we're used to. What's the nth cellular chains? I can write it as a big direct sum over all of the n cells. Really, I'm thinking finitely. If I was infinite, it'd be a big direct product over the n cells, and of the value of my abelian group, that's my coefficient system. In other words, my cells form a basis. Here, I've changed, I have a different notion of a point. Each of these is a point in the equivariant context. And then I just evaluate this on all of the possible notions of point I have. But it's restricted to exactly what shows up. So I'll do an example in just a second. Or maybe I'll have to go a little quicker. So at this point, obstruction theory works exactly the same way with this modification. This is the only trickiness for the obstruction theory. Now, this proposition that the obstruction cocycle, the thing that I've written down, if I wrote down the exact same thing here, the obstruction cocycle is again a cocycle. So I should have said the obstruction cochain is again a cocycle. And if I have things that are equivariantly homotopic, then their obstruction cochains are cohomologous. And I can do all the same thing. So what I want to do instead is think of the Braddon version and give you a way to compute. Or the homology version and give ways to compute. They work the same way. So let's say I have, well, the trick is we're going to copy the cellular homology story. So what was I supposed to do? Well, this actually tells me my cellular chains, this is how I'm going to define the cellular N cochains. And I need to tell you how to define the boundary map in order to understand this. So, I wonder if I'm going to have time. Maybe. So, if I take my n-1 skeleton, I have my wedge over the orbits. And then what I can do is project off onto the n-1 skeleton modulo the n-2 skeleton. So this is now a wedge over the orbits Tn-1 mod g of g mod h beta smash s n-1. So now when I apply my cellular chains, this
What's the notation HB plus?
H beta, so this was alpha in here, and this is beta in here. I didn't want to use the same alpha again. So now apply my cellular chain functor. Well, it's not really a functor. My cellular chain object. And that's the one that says, if I'm looking at an n-1 sphere, smash g mod h plus, give me the value of my coefficient system on g mod h plus. So I'll apply of this. Actually, I use any old coefficient system, m. And that gives me a big direct sum of over alpha in Tn mod g of m evaluated at G mod H alpha. And then this was just a map between two things that I could understand in that way. So this maps to the big direct sum over beta in Tn minus 1 mod G of M of G mod H beta. This is my cellular boundary map. All of these are determined by, if I take a single summand here, I include a single wedge factor in here, map over to here, and project off onto one of the wedge factors. That gives me a map that tells me each of the coordinates for this enormous matrix. But what I want to stress is this is actually a computable thing. This is an abelian group. This is an abelian group. M was not. M was this weird diagram. But when I evaluate M on any of the entries, G mod H alpha, oh, I'm sorry, my arrow went the wrong way. These are co-objects. When I evaluate this on any of the G mod H alphas, that gave me an abelian group. On the other hand, one second, I'll take your question. If I have a map from G mod H alpha to G mod H beta, that's a G map. That's a morphism in the orbit category. Morphisms in the orbit category are exactly the thing that M loves. This is the value of M on G mod H beta. This is the value of M on G mod H alpha. If I have a map from G mod H alpha to G mod H beta, then applying M gives me a map in the other way. That's this one. So this map, the cellular boundary map, is tied up in the value on the coefficient system, the actual structure maps that showed up in the coefficient system. So I'll try to do some examples. I'll have some examples for the problem session, and we can talk through some of them then, and then we'll keep building on this idea. This one's by far the hardest. I'm actually going to end up, once we stabilize, putting in more structure on these, and then it's actually much easier to compute. Because again, the extra structure means extra rigidity. All right, now your question.
So this matrix that's giving this map is indexed by alpha and beta.
Yes.
The rows and columns.
Yes.
And the value is going to be given by whatever the attaching map is, and it's going to be a value in the abelian group that M lands in?
It's going to, yes.
Okay.
Yes, exactly.
Okay.
I mean, I'm being slightly dishonest here because I ignored this sphere factor. Really, it's going to be, it is completely determined by the restriction map in this together with the degree of the map on the sphere part. And once you know that, you know everything.
So you just tensor with the that you get.
Yeah. So, exactly. I'll do an example, and you'll see how. Right now, it's very abstract, but it's actually very, very doable. Once you've written down a cell structure, everything that you would want, just like in algebraic topology 1, the moment you have a cell structure, it's easy to compute the homology. In fact, the hardest step is writing down a cell structure. Same thing here. Once I have a cell structure, it's easy to compute the homology. So, all right, I've run over time, so thank you for your indulgence.